What's good, guys? Welcome back to another video. Today we're doing another LeetCode problem. After this one, I'm gonna either do a new topic, or do more LeetCode, or go back to a previous topic, but just more advanced. Like let's say array, but slightly more advanced, so that I can start working on like the medium difficulty problem on LeetCode and stuff like that. Pretty cool. Or I can just do more different LeetCode. Why not? And then also towards the end, I will be posting a sort of like an outro kind of. It has like my other YouTube channel, my Twitch, and my Discord. So if you want to add me on Discord, if you have like a question or if you just want someone to talk to, there you go. You can just use that. Just add me and then, say that you saw me on YouTube or whatever. Yeah, so it's sort of like a small outro. I guess I created. Not, yeah, I mean, I didn't really put that much edit into it. It was kind of half-assed, but whatever. Okay, once again, I'm going to read the prompt, explain it, write out the code, explain line by line, and then read out, and then talk about the time and space complexity in the video. Okay, so question 100, same tree. This is a binary tree question, by the way. Given the root of two binary trees, P and Q, write a function to check if they are the same or not. Two binary trees are considered the same if they are structurally identical and the nodes have the same value. So looking at example 1, it's true, but example 2 is false because on this side, one dot left has a value, but one dot left does not. And then same with vice versa. One dot right has no value, but one dot right has a value. Okay. So this is very simple actually, because this is a very straightforward. You can just use recursion, so DFS. All you need to really check is the structure and value, like are they the same or not. So the key idea is that we have two trees. So let me write out the key ideas. We have two trees, a P and Q, and they are the same if, number one, both are null. So both are null will be same because they are both empty trees. Number two, exactly one is null. If that's the case, then not the same. Okay? Because let's say right here, there's a node 1 for P, but then there is no like node 1 for Q. So only exactly one of them is null. One of the tree is null. So they aren't the same. And then finally, 3 will be something like not null, right? They're both not null, or I guess I would say non-null. So if that happens, we want to do 3 things. We want to check if the values are equal. Very simple. All you have to do is p.val equal to q.val. And then afterward, you want to do you want to check left subtree are the same. By doing that, this is the part where we do the recursion, is by calling itself. And then check the p.left and right, and then p.right. And then finally, you want to do the right subtree, because if you do one for the left, you want to do the same for the right. So there we go. P.right, Q.right. Ooh, this part should be Q as well. There we go. All right, so, and that's it, really. So now I'm going to keep this here while writing it down. Let's do case number 1, which is what I mentioned. Both nodes are null. So when that happens, all we have to do is if P equals to null and Q is also equal to null, then return true. Because they are the same. If both sides has nothing, they're empty, they are legit the same. However, here's the other trick. Here's the other part. Here's the part where you have to write or instead. Because let's say if one side is true, like one P is null, but Q is not null. That means true or false, and then with the operation for or, a true or false is going to be true. A false or true is going to be true. True is true, false is false. So for this one, we want to make it false. So return false. Because if P is empty while Q isn't empty, that means the tree is not the same. They are not the same tree. So we have to return that false. Here's the third case. And the third case is where we're basically checking both non-null, right? Meaning they both have nodes inside of them. So we have to check the value. Does value match? Now we want to do p.val, and instead of putting equal, I want to do not equal to q.val. And when that happens, then we can just return false. So let's say, and this is sort of like the part where we check it, right? So if if it's 1 and 1, p.val is 1, q.val is 1. That means the value are the same. So when that happens, this if statement doesn't even work. However, let's say this part is a 1, whereas this part is a 2. Then yes, then 1 is not equal to 2 for the q value. So yes, that's when we have to return false. Now this is the part where we have to do the recursion. And we're gonna write it out as Boolean because we want just true or false, nothing else. Left same, and now this is the part where we call the function itself. Oops, there we go. Forgot this. And same thing with the right side. p.right, q.right. And after all of that, we just want to return the left same and right same. We want to make sure the and is there to check if they are like basically the same, you know. Because if left is false, right is true, then because it's an and operation, it's gonna come back out as false. Everything's gonna be false unless both are true. And that's it. And so honestly, there isn't really much to explain on like the lines because I've written out the cases. Except for this part, for some reason. There we go. Let's just write it like that. And then, okay, let's just quickly talk about the space and time complexity. Or should I do the examples? Oh, that's right. Keep in mind, just in case you want to, just in case you're asking like, hey, why is there a case 1 and case 2 like that? You gotta know that two binary trees are considered the same if they are structurally identical and the nodes have the same value, right? So structurally identical means that everywhere one tree has a node, the other tree must also have a node in that exact position. And one more thing, every one tree has no null, which is null. The other tree must also have no node. Okay? So if at some point, let's say tree P has a node, but tree Q has no node, right? Then that means the structure are different. And that means the tree are not the same. Damn, like sleepy. Okay, so let's do a quick example. So what we're going to do is we're going to call P and Q. Now we're going to check if P is 1, Q is 1, or when it checks case 1, are they both null? That is false. Because like there are nodes inside. And then Q, which is 1 by the way. Now case 2 is 1 null and the other is not. That is not true. So we skip. Both are non-null. Does the value match? So p.value, which is 1, q.value, which is also 1, does match. So this if statement is also skipped. Now we're going to do the recursion. Is same tree, p left, right left. So now we're on 2. And 2 is going to go through the process, same thing. And if 2 is for this if statement, 2 is equal to 2, so it's going to skip this if statement. Now we're going to check the p.left for 2 and q.left for 2. But this time they're both null. So when that happens, both you gotta know that both are null, and so the left subtree is gonna be like the same for this part. So 1, 2, 1, 2, they are both gonna be the same. And now we want to go back and check the right for 1 dot right and p dot right and q dot right. Once again, it's going to show 3. So when that happens, it's going to check. You can use the same logic. It's going to return true. And when that happens, afterward, you just want to return left same and right same, which are both true and true, which it gives you true because it's an and operation. So now you have to understand the space, just the time and space complexity. And it's very easy, actually. First, let n equal the number of nodes. Now, what we have here is time. In worst case scenario, we are going to have to compare every node once. So it will be big O of n. Big O of n for comparing every node at least once. Now, for space, because it's a recursion depth, and recursion depth is the height of the tree, so h. Recursion depth is the height of the tree h. So worst case scenario, it's a skewed, like a skewed tree, like this one, for example. This example 2, 1 to 2, that technically, even though there's only 2 nodes, it is like a skewed tree. So when that happens, that means it's big O of n. Like that. However, let's say we're on example 1, which is like a balanced case scenario. When that happens, the space complexity will be big O of log n. Like that. But yeah, anyway, that is it for the video. That I don't think there's anything else more to explain. If you have any questions, you can just basically go to the comment and type it out. I'll try my best to respond. Or you can just add me on Discord and ask me there. It's really, really up to you. Anyway, thanks. Thanks for watching. Bye. If you want to see another side of me that isn't always about computer science, then check out my other YouTube channel and come and watch my Twitch where I play a bunch of competitive games either by myself or with my friends. And not only that, but I do have my Discord available just in case if you wanted to add me either to just talk about anything, whatever you want, or have some kind of question from my video. Thanks.